What is electricity transmission? This transmission grid, which we're going to discuss in this class, is a highly complex and integrated network that transports large levels of electricity at a high voltage across large regional distances. Transmission lines are carefully designed and constructed according to strict design and operating standards. In North America, it's typically referred to the North American Electric Reliability Corporation, NERC, which provides oversight of the USA, Canada, and Mexico. All this to say, transmission grids are far more regulated than distribution grids. So, electricity transmission and that grid can typically be defined as a system for the bulk movement of electricity from a generator to a load area at high voltages. What is a load area? It's basically any portion of an electric circuit that consumes active electric power. Generators typically produce electricity at a low voltage. Therefore, prior to entering the transmission system, electricity is stepped up at substations, which increase the voltage, usually around from 13.8 or 14 kilovolts to 230 or 500 kilovolts. Transmission of electricity occurs at higher voltages because it minimizes the effect of transmission line losses. Once electricity is close to its point of use, a power substation is built where the voltage can be reduced through step-down transformers to distribution voltages below around 69 kilovolts. Voltage is then stepped down again at its final destination, usually at pad-mounted transformers or pole-mounted transformers, where it can be reduced down to 120 to 240 volts, which is used in a lot of households. As I mentioned before, the current governing body for all bulk power transmission in North America is NERC. NERC exists to ensure that the electrical grid is designed in a way that permits reliable, efficient, and affordable delivery of electric power. They oversee the amount of energy to be transmitted, the regional distances, design preferences, and then they use this information to determine the nominal voltages for a specific circuit. It also investigates and analyzes the causes of significant power system disturbances in order to help kind of prevent those future occurrences. Many of you will be familiar with the Enron example where electricity was shut off to areas of California, and that was being managed by a certain company that was basically autonomously controlling who was getting electricity and who wasn't to increase power prices. This is kind of the role that NERC serves. They want to ensure that there isn't that kind of monopolization of the grid and that there is no kind of bad play at work. So now let's talk a little bit about the differences between alternating current and high voltage direct current. Typical utility scale power plants, right? So these large power plants that are generating electricity will produce alternating current, and most electrical loads run on AC power. Thus, the majority of transmission lines, not just in North America but around the world, are of alternating current. There are many positives to using alternating current, the primary benefits being that AC power is more economical to generate. It's more economical to transmit over short distances. However, the challenge is that to transmit alternating current, it is vulnerable to instability and unscheduled flow problems. High voltage direct current is not as ubiquitous as alternating current. It is, in many respects, actually a more economical means of transmitting bulk power. It is also better at ensuring system stability overall by essentially preventing cascading failures. And I'll talk about this later in a future course. But direct current is highly controllable, and it can be used between non-synchronous power systems, right? It's easy to adjust between different power systems, much more than AC. However, the challenge with transmitting high voltage direct current is that two converter stations are needed. First, the alternating current must be converted to direct current to begin the transmission process. And then when it gets to the desired destination, the direct current must be converted back to alternating current again to be used on the grid. So some pros of high voltage direct current: more power per conductor, less wires and towers, and easily managed power flow. It's also a little bit more economical over long distances, though if you're accounting for the fact that you need to have two converter stations, it can be costly in some respects as well. Some cons: cannot be easily converted to high or low voltages. It also requires those converter stations, which I talked about, which are also expensive. So the economics for alternating current tend to have won out, not just in the North American electrical grid, but in the international electrical grid. And we're going to talk about this in the assignment this week as well.